Problem B2. Solid heat. In classical thermodynamics, a solid containing n atoms has a heat capacity CV equals 3n kB, Boltzmann constant. The two parts of this question are independent. In both parts, we assume the solid has constant volume. Question A. In a simple quantum model of a solid, the energy is E equals h omega m, where m is the number of quanta and omega is a constant. Einstein showed that the entropy of such a solid is expression 1 up to a constant. According to the first law of thermodynamics, dE equals T/ds for this system. Part 1. Find an expression for m in terms of n and the quantity alpha equals h omega over kBt. Part 2. We want to see how quantum effects modify the familiar classical result in the limit alpha much less than 1, where the quantum corrections are small. Write an approximate expression for m, including terms of order alpha but neglecting terms of order alpha square or higher. Part 3. The heat capacity, with its leading quantum correction, is CV approximately equal 3n kB multiplied by 1 plus b a power n for some constants b and n. Find the values of b and n. Question B. A vertical cylinder is filled with a monatomic ideal gas, and capped by a movable piston. The temperature is high enough for the piston to be modeled as a classical solid. The gas and piston contain the same number of atoms, but the mass of the gas is negligible compared to that of the piston. Assume the entire cylinder is in vacuum, and that the gas and piston do not transfer heat to their environment, but always remain in thermal equilibrium with each other. Part 1. When the piston is in mechanical equilibrium, the column of gas has height h and pressure, P equals P0. At this point, find dP over dH in terms of P0 and h. Part 2. If the piston is given a small vertical impulse, what is the angular frequency of its subsequent oscillations? Give your answer solely in terms of h and the gravitational acceleration g.